All right, good morning, everyone. We're looking at page 35 and dealing with something called mechanical energy today, and also what's called the law of conservation of mechanical energy. There's a definition that we need to be familiar with, and regardless of what you see when you read the words mechanical energy, it has a very specific physics definition or meaning. It's the sum of the potential energy and the kinetic energy that an object has. And I want to make a point here because later on you might be confused about this. This is the sum of the potential energy at one specific point in time. We're going to be talking today about, among other things, pendula. Pendula is plural of pendulum. And when a pendulum is swinging, when it's at its highest point, it's not moving at that instant in time, but it does have potential energy. And when it reaches the lowest point, it's at its lowest point, so we can say it does not have potential energy, but it has kinetic. I'm not saying that the mechanical energy is the potential energy that it has at the top plus the kinetic energy it has at the bottom. That's not what I'm saying. In fact, for a pendulum, whatever potential energy it has at the top, that's the mechanical energy because there is no kinetic. Or whatever kinetic it has at the bottom, that's the mechanical energy because at the bottom it has no potential. Whereas if it were partway through its swing between the top and the bottom, it's moving, so it has kinetic energy. It's above its lowest point, so it has potential energy. And what that means is that at that point, in between the highest and lowest points, its mechanical energy would be the sum of those two things. So just a quick note here, because I know some of you will be looking at this notation. That is a Greek sigma. It's a capital Greek letter sigma, and it's used in science and math to mean total. Okay? So that's all that means. So, talking about a pendulum, if I take a pendulum and I release it from the highest point, and this fluorescent safety tape here is here so that you didn't walk into the rope on your way into the classroom, but it's also there so that if you're on the far side of the room, you can see the pendulum moving. The pendulum at the highest point, which is right there, stops momentarily. And it has potential energy at the highest point. But at the lowest point, it has no potential energy because it's at its lowest point, so it has kinetic energy. But what is important today, this is what we're going with, is if you look at the screen now, the mechanical energy the pendulum has at this point, the mechanical energy that the pendulum has at this point you can see on the screen, and the mechanical energy it has at this point, and the mechanical energy it has here, and here, and here, and here, and here, it's going to be the same all the time. But, and I know I haven't actually taught this to you, but I think you can figure it out. When would it not be true that that mechanical energy is going to be the same everywhere? I mean, what I'm saying is whatever the potential energy is at this point, whatever the potential energy is at this point, and whatever the kinetic energy at this point is, they have to be the same because the potential energy decreased and turned into kinetic. When would that not be the case? Mark, do you have an idea? What? Say that again. That's perfect.
When another force acts on it.
When there are other forces acting on it, outside forces. And if there are outside forces acting on it, like the force of friction, or whatever, a big wind comes up and starts pushing the pendulum in one direction, those outside forces no longer conserve that mechanical energy. Most people would say, I'm glad you said that. That feeds perfectly into where I'm going with this. Most people would say if there's friction, and that's an outside force. Okay? If energy is conserved, if mechanical energy is conserved, can it ever rise, when I release it from here, higher than where I released it from? No. So that means if I stand here and put it against my chin, I have faith in physics. I know it's not going to hit me. If anything, there will be a little bit of frictional force up at the top on the ceiling where that string is rubbing, where that rope is rubbing. So if anything, I know that it's not going to rise up to the same point. But no matter how many times I do this, I either flinch physically or in my brain I flinch, like I close my eyes. And it's really moving, isn't it? See, I kind of stiffened up there. Take a look at where it goes to for the highest point. It was hitting my chin. Is it going to hit my finger? No. So it does lose some energy. It's not a perfect system. And later on, we can certainly get other people to try it. Okay. If, on the other hand, I released it from here and I gave it a little push, then it probably would have hit my chin if I didn't move out of the way. In the next unit, you're going to be doing experiments with pendula because it turns out there's a relationship between the length of the pendulum and the time it takes to go back and forth. This is very interesting. If we were to maybe get your phones out, we'll do some measurements here. What you were going to do, and I'm leading up to unit 2, we'll get back to energy in a second, is I'm going to set the pendulum in motion. And what we want to do is measure the time it takes. Just wait to hear it before you start timing. The time it takes to go from the highest point back to the highest point. But let's do 5. So you would go start, and we would count 1, and then when we get to 5, we would finish. Okay, so we'll start when it comes back to here. Start. That's 1. That's 2, 3, 4. You're going to stop when it hits the highest point again. 5. Georgia, do you have a time?
16.24.
Can you divide that by 5, please?
3.248.
3.248 seconds. Jordan, what did you get?
My time's went wrong, so I didn't get a time.
Okay. Abby, do you have one?
15.72.
And when you divide by 5?
3.144.
3.1, 3.2, let's call it 3 point. It doesn't matter. What about if I get it in motion now? I want to get it straighter. Now most of you can't see the pendulum ball, but you can see the caution tape on it. Let's do it again. So you're going to start, when it comes back, you're going to go start, and we're going to count 1, 2, stop. Georgia, what did you get?
15.49.
Divide by 5?
3.1.
So you got 3.2 last time. This time you got 3.1. Abby,
15.65.
divide by 5?
3.13.
So you got 3.1 last time, 3.1 this time. It turns out that the period is not affected by how far you move it. However, and I know I'm getting off topic. This has nothing to do with today, but we're here to learn, right? smart, eh? I could give Wile E. Coyote a run for his money. But if I measure the period now, I mean, it's pretty obvious it's a smaller period of time, isn't it? I'll do that again. So we can start at the highest point. Next time around, we'll start. Now, it's 1, 2, 3, 4, 5. Abby, divide your total by 5 and let me know what you get.
2.22.
Less, right? If I did this, I got kind of going in a circle. I don't want that. It's obvious here. Just estimating 1/1000. It's less than 2 seconds. If I do this, that's kind of interesting that the longer it gets, I mean, it kind of makes sense. But that was the same pendulum, and all I did was I decreased the length, and all of a sudden, it takes less time. Anyway, we're going to study pendula in detail later, and there will be a lab you'll do where you can actually determine the acceleration due to gravity by measuring these things. Let's get back to what Mark said, though. When would this energy start decreasing? Well, it would decrease if there were outside forces acting. So we have a new definition here. This is called an isolated system. It's one in which no outside work is done to the object and no energy is lost. In other words, no outside forces are acting. So if no outside forces are acting, and even if we just put this here, and I know as a teaching method this is not wise because you're going to be watching this and being hypnotized by this while I'm trying to explain stuff. If you were to look at the height that that pendulum is reaching, and I have it kind of going in a bit of a circular fashion, I don't want that. If you were to look at the height it's reaching and just make a mental observation that it reaches kind of about the height of the desk, and then let's forget about that for a few minutes. Is this an isolated system or not? Well, let's continue here just for a minute. If there is friction, which is an outside force, it's going to produce heat. Is there friction with that pendulum and anything else? Where's that friction happening? Air. So there's friction between the air and the ball. And you can already see it's not rising to the same height, is it? So we're losing energy already because there's an outside force. Is there another force of friction acting on that pendulum? Joseph? Right, the pivot point. And you know, if you look carefully, that rope that I've got tied through that series of hooks with the clips, it's actually rubbing. The rope is turning against that surface and rubbing. So what ends up happening is you get friction. However, just in swinging back and forth, energy is pretty much conserved. So in an isolated system, mechanical energy is conserved. You might have an object which loses kinetic energy, but if mechanical energy is conserved, if it loses kinetic, it has to gain the equal amount of potential. So the mechanical energy can be transferred from one object to another or transferred from one form to another, but the total kinetic and potential, which is mechanical, cannot change. And that's the law of conservation of mechanical energy. So everything we do today assumes mechanical energy is conserved. Everything we do today assumes there are no outside forces present, like forces of friction. So examples, what is the relationship between the potential and kinetic energy an object has when sliding down a frictionless inclined plane? Well, let me show it to you first. Please don't attempt to draw all of this. We'll write down an answer in a second. But right now I'm holding that red object at the top of the ramp and I'm about to release it. Does it have mechanical energy? Yes. What form of mechanical energy does it have? 100% gravitational potential. But I let it go and I take a snapshot of it a short time later. I'm not stopping the object. This is a snapshot. And at that instant in time that's being shown, it's moving already. which means it has some kinetic energy. But if you look carefully, what's happened is the amount of kinetic energy it has is the potential that was lost. You understand, of course, that it doesn't go from being here to here. It's a gradual thing. It doesn't disappear and then appear someplace else. And as it continues sliding down the ramp in different locations, it will be closer to the minimum height where there's no potential energy, and it will be moving faster, and eventually the amount of kinetic energy it has at the bottom will be the potential energy it has at the top. And we can answer this question now in a very succinct way with an equation. That the gravitational potential energy it has at the top is equal to the kinetic energy it has at the bottom, which is in fact equal to the potential energy it has plus the kinetic energy it has anywhere. I'm saying if you take any 2 points in the journey of that box down the ramp, and it's frictionless, which is, a dream. But if you take any 2 points, whether it's the top and the middle, the top and the bottom, or 2/3 of the way down and 9/10 of the way down, the total kinetic and potential energy at each of those points will be the same. And this brings up a very important idea. That, you know what, I'm going to go back and just talk about this for a second. This isn't an example in your notes, but this is a question we could have done in the previous unit where I said, what is the speed it has at the bottom? But what you would have done in the previous unit is you would have drawn a free body diagram to find the net acceleration down the ramp. Then you would have used kinematics along with the distance or length of the ramp, and you'd have to use trig in there to find the parallel component of gravity. Whereas if I just told you this was, I'll go with 30 degrees, and this is 8 meters, rather than doing all of that, you could say that mgh at the top is 1/2 mv squared at the bottom, and you don't have to worry about forces or vectors or free body diagrams or anything. You don't even have to worry about the acceleration. The masses cancel, and you're left with v squared equals 2gh. All you have to do is go 2 times 9.81 times 8 and take the square root and you have your answer. No more free body diagrams. Wow. In this question, you could do it without free body diagrams. Okay, let's take a look at an example. On a frictionless roller coaster, a car with a mass of 800 kilograms has a speed of 4 meters per second when it's 35 meters above the ground. Later, its speed is measured to be 2 or 20 meters per second. What is its initial mechanical energy relative to the ground? Well, mechanical energy is 1/2 mv squared plus mgh. So this would be 1/2 times times 800 kilograms times 4 meters per second squared plus 800 kilograms times g, we all know what g is, times the height of 35 meters. Well, get your calculators out and calculate that. I'm getting 281,080 joules. Same number? Okay. So the mechanical energy, and I'm not concerned about significant figures here at all, is 281,080 joules. B, What is its gravitational potential energy in the second instance? Well, that's kind of a weird question because gravitational potential energy is mgh. But we don't know. We don't know how high above the ground it is later. We know how fast it's moving. And by the way, you can't solve this with a free body diagram because the roller coaster is not a ramp. It's going up and down, or it's got a curve to it. The forces are always changing. But what we can say is that later, in the second instance, it does have kinetic energy. Can we find its kinetic energy afterwards? Well, sure, we have the mass of 800, and it's moving at 20 meters per second. So we're going to square that. Now, before you do any calculations, do you agree it's moving faster later on than it was to begin with? That means it has more kinetic energy, which means it must have less potential energy. Keep that in mind. What does this work out to? I want to say this is 160,000. 160,000 joules. So how can we determine the gravitational potential energy afterwards, which is what it's asking us? How are we going to do that? Jacob.
Subtract the kinetic energy we just got from the mechanical energy from the first.
Right. The mechanical energy we got of 281,080 joules, did I remember that correctly? That's the sum of kinetic and potential. And it doesn't change as the roller coaster goes to different positions. It hands off some of the energy from kinetic to potential or potential to kinetic depending on what the roller coaster is doing. So this has to equal the sum of these two. So yeah, we're going to take 281,080 and subtract 160,000 because that mechanical energy is always equal to the kinetic plus the potential at any specific point in time. So at the beginning, that point in time it had that much energy. Here, at this point in time, it also has that much energy. So 281,080 minus or equals 160,000 plus EP. And you don't have to set up a formula. I mean, what you did was you just used common sense. I better subtract them. And what I get is 121,080 joules. So this is the gravitational potential energy. Any questions with B? All right. An ideal pendulum, what does the word ideal mean? It means we're going to assume there's no friction. We're going to assume that energy is 100% conserved. Mechanical energy is 100% conserved. It is suspended by a string that is 2 meters long. It's pulled sideways and released. And at the highest point of the swing, the pendulum is 25 centimeters above the floor. At the lowest point, it's 5 centimeters above the floor. Well, let's draw this. This is what it looks like. So I've got the floor there. I just want to look at my numbers again. This distance is 5 centimeters. And this distance is 25 centimeters. Are you with me on that? Did I get the numbers right? Okay. So that's what we are looking at. And I drew my heights to the bottom of the pendulum. You could have drawn your heights to the middle of the pendulum. You could have drawn it to the top, as long as you're consistent. What is the mechanical energy of the pendulum relative to the floor when it's at its highest point? When it's at the highest point, and we've already seen a pendulum today, at the highest point, there is no kinetic energy. But at the highest point, because it is above the ground, there is potential energy. At the highest point, and this is maybe the most important thing so far here, at the highest point, whatever potential energy it has is the mechanical energy, because there's no kinetic. And this is just MGH. This is child's play. We're going to take M times G times the height above the floor, which is 25 centimeters. We have to convert it to meters, of course. So EP is 0.25 kilograms times 9.81 newtons per kilogram times 0.25 meters. I get 0.613. So it has 0.613 joules of potential energy at the top, which means the mechanical energy is 0.613 joules. I hope everybody knows this, but I want somebody to tell us, why is the mechanical energy equal to the potential energy? Caleb? Because there's no kinetic, and mechanical is sum of kinetic and potential. Okay, what is the mechanical energy of the pendulum relative to the lowest point, or relative to the floor when it's at its lowest point? Well, we do the same calculation. Well, do we have to? Just a second here. Let me just stop. We're not going to do the same calculation. It's not asking for the potential energy, it's asking for the mechanical energy. So what is the mechanical energy at the bottom of the swing? Jordan. I'm asking for a number. I'm asking actually for a number here. Mark? Same number, right? 0.613. Because mechanical energy is conserved because it's an ideal pendulum. Now, I want to just ask you a question here. It says, what is the kinetic energy when it's at the lowest point? This is the question I was going to ask, but it's already here. It's not 0.613. Because when we measured the potential energy, we were measuring it relative to the floor. So, over here in this diagram, at the top, all of its energy is potential. At the bottom, it has both types of energy because it's still above the floor, which is a bad move. You're going to learn something from this. Okay, and we'll get to the good move in a second. So, at the bottom, it still has potential energy because we measured everything relative to the floor. And what that means when we do C is we're going to take that mechanical energy and set it equal to the kinetic at the bottom and the potential at the bottom. But the potential at the bottom is not zero. This is the mass times G times the height above the floor. .25 times 9.81 times 0.05 gives me, it still has some potential energy there. It has 0.12 joules. So what we have is 0.613 joules. The total energy is the kinetic energy it has at the bottom plus that 0.122 joules it has that's potential. So in order for me to answer this question, I need to take the mechanical energy in the system, which is this number, and subtract the potential energy it has at the bottom, and this is the kinetic energy it has at the bottom. 0.4905. So EK at the bottom is 0.4905 joules. So what is the speed? Well, that's pretty easy because the kinetic energy is 1/2 mv squared. Do you remember me telling you either yesterday or the day before that between physics 20 and physics 30, you will be using the kinetic energy formula to find a speed over 100 times? You got to get into the rhythm of this. You take the energy times 2 divided by the mass and then take the square root. So times 2 divided by 0.25 and take the square root. About 2 meters per second. Let's just call it 2.0 meters per second. So before I show you the wiser road to walk down, does anybody have any questions with A, B, C, or D? Yeah.
How come it gives us the length of the string that we use?
I don't know. It's not needed. It's certainly not needed. When we look at the diagram, there is nothing in this diagram that we would need the length of the string for. Sometimes, Ethan and everybody, what you will be told instead of this height, what you will be told is this angle, and you can use that angle with the length of the string to find out where it is above its lowest point in space. But we didn't need it here. Sometimes, and you're going to have to get more and more used to this. Sometimes you're given information that you just don't need. It's not obviously unneeded, like, by the way, Mr. Way had steak and lobster last night for supper. That obviously you wouldn't use that. But sometimes there's physics information that you don't need. Okay? Any other questions with A, B, C, or D? Okay, so now let me cut to the chase here. D is what you would be asked to find. Okay? So if you were asked to find the speed, and we go back to this information in the question, and we construct this diagram, the wise move would be for you to say that this is 0. Because then if that's 0, you can use 0.2 meters there, because this was 5 centimeters and this is 25 centimeters, so the difference is 20 centimeters. And the reason why that would be a wise move is then you would simply say the mechanical at the top and the mechanical at the bottom are the same, which means you can do that. I mean, I think it's important you understand what it means to say mechanical energy is conserved throughout. But you're done. Cancel the masses. And the reason why this works is if you're saying height is 0 here, then you are saying what Jordan initially said, which is that at the bottom, the kinetic energy will be the potential energy at the top. Because at the top, there's no kinetic energy, and at the bottom, there's no potential. That means the potential at the top and the kinetic at the bottom have to be equal. And you can just confirm this. Take 2 times g times 0.2 and take the square root. And, you know, it's not that it's even close. It's the same answer. All right, let's try another one. A mass slides down the frictionless ramp from the top. What is the speed at the bottom? It doesn't say from rest, and it should. Okay? What this means, and I think I've set the stage for this, is that I'll try it in a different way. EK plus EP at the top and EK plus EP at the bottom are equal, but at the top, this is 0, and at the bottom, this is 0. So you're left with potential energy at the top equals kinetic energy at the bottom. You're left with mgh equals 1/2 mv squared. Do you know the mass? Yeah. Do you need to know the mass? No. And if you did this with dynamics and free body diagrams and combined it with F equals ma and kinematics to find a final speed at the bottom, you would get it. The only obstacle here is that you don't know h. But that's trivial. That's a grade 9 or grade 8 Pythagorean theorem question. 8 squared is 64. 6 squared is 36. 64 minus 36 is 28. So the height is whatever the square root of 28 is. You would do this on your calculator. So v squared is 2gh, which means v is root 2gh. And that's going to be your answer. You know, I could have just led with this. I could have just said, explained in words for 5 minutes what's going on and said, okay, let's start with this example. But I do think it's important you understand where it comes from. That the total energy is staying the same. The total mechanical energy is staying the same. It's just that it's trading off from one type of mechanical to another. So what are we getting here? Let's see. Well, let's figure out root 28 first. Don't worry about how I got root 28. It's 5.29. So 2 times 9.81 times the answer. Take the square root. That seems awfully high, but I would double check it. Well, that's a lot. That's a big distance, though. 10.2 meters per second. I will just say 10 meters per second to keep in line with the two significant figures in the question. Any questions with 4? A number of years ago, I was trying to draw something in Microsoft Word, and that's how it came out. And I kind of like it. It's kind of Escher-esque. Escher is an artist who does really weird drawings. Nicer than that. But that's a roller coaster. There's a couple of people in the roller coaster peeking out. And the roller coaster passes the highest point with a speed of 15 meters per second. What is the speed when it's at the 33-meter height? Well, our smart move here would be to say that we're going to consider that to be 0. What that literally means is when it passes the 30-meter mark, it actually has a negative amount of potential energy because it's lower than the lowest point. That's an idea we use in Physics 30 sometimes. So I'm going to tell you that the speed it will have when it follows this path, the speed it's going to have at this point here, is the same as the speed it would have at that point if it followed this path. And it's the same as the speed it would have if it followed this path, a direct path. It doesn't matter what happens in between because mechanical energy is conserved. So all we're going to do is say that the mechanical energy at the top, let's make this easier for ourselves. Let's call this point A and this point C. the mechanical energy it has at A and the mechanical energy it has at C are equal. But due to our wise choice of where we're going to measure the height from, EP is 0 there. This will be 1/2 mv squared at A plus mgh at A. This will be 1/2 mv squared at B. Sorry, at C. So before we do some calculations, any questions with the setup? All right, well, looking up here, please, we can cancel the masses. Presumably nobody fell out of the cart on its journey. The mass is the same the whole time. I don't like fractions in equations, so why don't I multiply everything by 2? I'm going to multiply this by 2. I'm going to multiply this by 2 and this by 2. And I just want to do this because it's going to make our jobs easier. We will get V at A squared plus 2GH equals V at C squared. And just because that's pretty spooky. Because that equation I just wrote is a kinematics equation that's only valid for objects accelerating in a straight line. But it has the same structure. Is this G in the formula that's in brown the actual acceleration of the car? I hope not, because then it's in free fall. But it looks the same. It would be wrong to solve the problem using this formula in faded red, because that's not what's happening. But you would get the right answer. So, we're going to put, what is the speed it passes at? 15 meters per second. I'm going to leave the units out today for this. 2 times g, we know what g is. What is h? What is h? Well, h is not 33 meters. H is not 40 meters. H is the difference between them. 7. This is h at point A, because it's above h equals 0. If you don't do that, then you would use 30 here, but you would also have an mgh on the other side. Sorry, you would use 40 here, and you would have another mgh on the other side of 33. I think 33. Yeah. But it would all work out mathematically. So this is a pretty easy question to solve. Once you understand the physics and set it up, you go 2 times 9.81 times 7 plus 15 squared, and you take the square root. That's it. Again, what we want to do in physics is we want to use our understanding of physics to develop a formula, and then it becomes a math thing, right? So physics 30 is not me giving you this formula and telling you what h, g, and v at A are and getting the problem. Physics 20 and 30 is you finding this formula. 15 squared plus 2 times 9.81 times 7. Take the square root. 19 meters per second, which is a heck of a ride. It also means, by the way, it would have been going faster in between, because it goes lower than that in the middle point. One final question. This is going to lead up to the next lesson. I'm just going to help you out here. Turns out this is 3.75 meters. You can go ahead and add that in. If you wanted to use trigonometry to find it, you could, but I want to just get that out of the way. It's not important. What is the potential energy of the box at the top? Potential at the top. Not mechanical, potential. I would like you to calculate the potential energy it has at the top. Pretty straightforward calculation. 12 times 9.81 times 3.75. $441.45 joules. Who can tell me how much kinetic energy it has at the bottom? That number? No. You're told the speed at the bottom, aren't you? I kind of covered things up here a bit, so maybe you didn't notice that, but you know the speed at the bottom. So if you know the speed at the bottom, you can find the kinetic energy at the bottom. What are you assuming if you automatically assumed the answer to B was 441.45? You were assuming mechanical energy is conserved. But nowhere in this question does it say it's frictionless. So what we're going to do, this was found using MGH. We're going to do the same thing down here. We're going to find the kinetic energy using 1/2 mv squared. Which again is when I say it's a trivial calculation, I mean it's an easy calculation. It's an important one, I guess. That's 1/2 times the mass, which is 12, times the speed squared, which gives me 216 joules. Are you getting the same number? Okay. What's going on here? Have we broken the laws of physics? Have we discovered a loophole in what I've taught you today? No. We have less energy. Well, let me back up. This is the mechanical at the top. Again, it should say from rest, so I should change that. That's the mechanical at the top, because at the top it's all potential energy. This is the mechanical at the bottom. So, like I said, we haven't found a loophole in the rules that govern the universe. What we have just run into is an example where mechanical energy is not conserved, which means it's not an isolated system, which means there's other forces involved, most likely the force of friction. And I'll maybe show you how you can calculate the force of friction from this. It's pretty simple. It's a simple calculation. Conceptually, it's more difficult. So, what's the heat lost by friction? Well, if you started off with mechanical energy of 441.45 joules, and then you have mechanical energy of 216 joules, then you've lost mechanical energy. The only, as far as we're concerned, the only place mechanical energy can go if it's lost is heat energy. So when we subtract these two, we get 225.45 joules of heat. Good morning.
I just got mixed into two of my stacks.
Oh,
Sorry.
thank you. That's okay. Bottom line here in this question, since the mechanical energy at the top is not the same as the mechanical energy at the bottom, mechanical energy was not conserved, which means it's not an isolated system, which means there are outside forces, and the force happens to be a force of friction. But this number we found is not a force of friction. It's the heat produced by friction. I stressed this before, but I want to stress it again. Friction is a word we use to describe a force. Heat is the word we use to describe the energy that that force produces.